Do a little trivia. Let's say we have the exact same refrigerant in both of these tanks. Let's say it's 410A, and we know the room temperature of the tank. And as long as there is liquid and vapor, we're going to be at saturation. So if we know the temperature of the tank and we know there's liquid and vapor, we can tell you exactly what the pressure is going to be because it matches the temperature pressure chart. It follows saturation. So if I have, say, 50% liquid, 50% vapor here, 50% liquid, 50% vapor here, and it's in the same exact room temperature, there'll also be the same pressure. But let's see what would happen if I was to hook a hose to this refrigerant tank and also hook a hose over here to this refrigerant tank. And I was to open both these tanks up. What do you think would happen? The answer is nothing, because there's the same amount of pressure in both of these tanks. So there would be no flow. It would be the same temperature. There's liquid and vapor. We know what the saturation is going to be. We could follow it. We could map it. If you want to try it, let's say this room temperature right now is about 95 degrees. So if we have 95 degrees and we know there's liquid and vapor with 410A, we can find out exactly what the pressure is going to be. So it's 95 degrees. If I had at least some liquid and vapor, that means the pressure would be about 299 psi gauge. 299 psi gauge. So that's a significant amount of pressure, 299 psi gauge. So there would be no flow, the same pressure in both of these, nothing would happen. Trivia question number 2. Let's say this one is filled at 80% capacity, the max we could ever fill it. And this one is only at, say, 10% capacity. But there's still liquid and vapor, only 10% liquid. And this one was 80% liquid, but they are still in the same room temperature. They're still at saturation. It's still 95 degrees in here. What do you think would happen? And the answer is, again, nothing, because there's the same exact pressure in both of these tanks. There's nothing to push the refrigerant from one way to the other. The tanks are equalized. The pressure would be equalized. So let's think about something a little different. What about if I was to heat this tank up? I was to submerge it in hot water or warm water, which is a safe way of raising the temperature of the tank. Now I was to increase the temperature of this tank. Now what do you think would happen? The answer is refrigerant migration. The temperature of this tank would increase, also the pressure would increase. So the liquid refrigerant would start to migrate out of this tank and it would start traveling towards this tank. So eventually they would come to an equalization, a point to where they're both the same, but refrigerant likes to migrate to the cooler location. So it's going to leave the warmer area and hang out in the cooler area. So that's one way we can do it. We can heat this tank up and we'll see it migrate over to the one that never changed. But there's yet another way of doing it. Let's start over. Let's say they're both at the exact same temperature, 95 degrees, and we have liquid and vapor in both these things. Let's start over with 50% liquid, 50% vapor. Both tanks are in the same room temperature. And I was to take and put this one into a bucket of ice water. So the temperature of this tank is going to drop. So the temperature of this tank drops, the pressure is also going to drop. But we have them connected with the hose. We're going to end up with refrigerant migration. The refrigerant from this tank is going to start migrating over to this tank. Refrigerant likes to migrate to the place that it's cooler. I actually talked to one person that worked for a laboratory, and they were able to do refrigerant recovery just simply by hooking a hose up to the unit and putting the tank in liquid nitrogen, or putting liquid nitrogen on the tank, and it dropped the temperature of the tank so dramatically, all the refrigerant would migrate out of the equipment and go to the tank. It's another way of doing recovery. No pump at all needed. So refrigerant likes to migrate to the cooler place. It's called refrigerant migration. It's like, hey, it's cool over here. Let's all hang out over here. And all the refrigerant will go this way. As a young tech, I didn't know that. And I had daisy chained many different recovery tanks together. So there's 2 ports. So I had this port just like this is connected. And I had another port to another tank, another port to another tank. I had like 8 or 9 connected. And on the tank at the very end, I had a hose from this tank to my recovery machine, putting it into a very large commercial tank. I thought, great, I can save time. I can have it pulling all of these. It's going to take a good part of the day to do that. I can go do something else. Well, I went to lunch. When I came back from lunch, what I found was really surprising. This tank was completely full of refrigerant, and this tank had a lot of refrigerant in it, and the others were almost completely empty, only vapor alone. What was happening was, as I was pulling refrigerant out of this tank, the refrigerant that remained boiled into a vapor. As it boiled into a vapor, it caused it to absorb heat. So the temperature of this tank started to drop. So refrigerant started migrating this way. Well, this tank, as it was migrating over to this tank, we had the same thing. Refrigerant was boiling from a liquid into a vapor. So the temperature of this tank was dropping. So all the other refrigerants migrated into these two tanks that was completely full, which really panicked me because this tank should never be over 80% full. If it's over 80% full, it could have an issue of expansion and it could rupture or explode. So it was a kind of a big deal. I had to sit there and baby it to make sure I got the refrigerant out of that tank to make sure we didn't have a safety issue. So if I was to shut the pump off and take this outside, since it's completely full of liquid, as the temperature started to increase, the refrigerant would start to expand and it could potentially become a bomb. So refrigerant migrates to the cooler location. That's important. Let's apply this to the next thing I want to talk about. So let's think about a scenario. We have a commercial building, let's say an airport, and the temperature outside of this airport starts to drop. But inside the airport, there's people going everywhere. There's equipment, there's people movers, there's elevators, there's lots of restaurants going, there's a lot of heat inside, so they still need cooling. Well, the temperature outside where the compressor is going to be a lower temperature. So the system cycles off, and where does the refrigerant want to do? Well, it wants to go to the cool spot. It wants to hang out with the cool kids. So all the refrigerant will start to migrate over to the compressor. And as the refrigerant migrates to the compressor, it soaks in with the oil. And that causes two problems. When this compressor does start back up, we have issue number one. We now have liquid refrigerant going into our vapor pump, and something's going to break. And problem number two, as the refrigerant mixes with the oil and we start our vapor pump up, that refrigerant starts to boil out of the oil. As it starts to boil out of the oil starts to become foam. If you've ever kind of taken bubbles, you've blown bubbles, that's what's happening. All these foam, all these bubbles. So the oil level starts to drop as all this foam starts rising. Well, as all this foam starts to rise, we have two problems. Problem number one, we end up at the bottom, no oil to lubricate those bearings. And problem number two, we get all the oil into the pump action. So that's a very bad thing. So we want to make sure that we prevent that from happening. There's also, later we're going to talk about heat pumps. And heat pumps are going to be where the compressor is operating outside when the temperature is low. So as soon as this unit shuts off, the refrigerant is going to want to migrate to this compressor. So there's ways that we can stop that. And what we use is what we call a crankcase heater. So this is a external crankcase heater, and I call these belly bands. I don't know the proper name of it, but it's cool because they look kind of like a hose clamp, a really giant hose clamp with the wires on it. And we put this at the bottom, crankshaft in the very bottom, and this was the crankcase. Well, this is a scroll, so it didn't quite have that, but we could put this around and then tighten this up. And then we wire this up to the system. Now what this is doing is keeping the crankshaft warm, or the crankcase warm. We're keeping the oil warm. And if we keep this warm, we can keep it just warm enough to prevent the refrigerant from wanting to migrate to this lower temperature oil. This is a very common one. This is very easy to replace, but they made another type as well. They made a type that looked like this. Still had two wires on it, but they would have a type of a well drilled in there. And this little piece here would slide inside of that little well. So when you're looking at it, you're only seeing this end of it. You're not seeing all the other part. And there'd be some type of little snap ring or keeper ring in there, and you could take it out to replace it, but it did the same thing. We allowed electricity to go through here, and we kept the system warm. We kept the oil warm. There's several other types of them, but the whole idea was to prevent refrigerant migration. So if we kept this crankcase warm, refrigerant was less likely to want to migrate to it. Now the other thing is refrigerant also likes to migrate to the oil. So even if the temperature outside is not that low of a temperature, refrigerant can still want to migrate to this oil. When I was a younger tech and I was working in Florida, I would see these shorted out all the time, and I would just cut them loose and be like, hey, you don't need to worry about that. And I thought I was saving the customer money. But really I was putting their compressor at risk, because even though it wasn't working at a low temperature, it's still possible for that refrigerant wanting to migrate to the oil. So by having a crankcase heater, it keeps the oil warm and keeps the refrigerant, the liquid refrigerant, out of this crankcase. Another important thing about crankcase heaters, most of the time we want to have it where a crankcase heater is only heating when the unit is off. When the unit's running, we don't need it. Remember, the reciprocating compressor had the discharge line run all the way into the bottom just for that purpose. So when the system is running, I don't need to spend money buying electricity to heat up this oil and then spend money taking the heat out of the oil at the condenser. So we typically want to see these wired to where when the system is off, the crankcase heater is on. When the compressor is running, the crankcase heater is off. We're going to talk about how to wire that and the many different ways of doing that later on when we get to electrical. Now there's yet another way of doing it. Some use a combination of this as well as powering the windings. When we talked about all those electrical windings inside the one that was cut open, we could actually send a small current through those windings. And it's not enough to make the motor run, but it's enough to create some heat. And we're actually using the windings inside that compressor to create enough heat to also help prevent refrigerant migration. Sometimes we can wire them to where just the windings in the motor stay warm. We could also wire it to where the windings work with a crankcase heater to keep the windings warm and also the case of this warm. So a few little cool things about it. We want to prevent refrigerant migration to our compressor. So we use a crankcase heater. This is just two of the styles. There's many different types of them, but they typically have at least two wires. We want to make sure we prevent refrigerant migrating to the cooler compressor and we prevent it from migrating to the oil. That liquid refrigerant damages the compressor itself and also causes the liquid oil to foam up to where you have poor foaming and the oil can then flood the compressor. We want the crankcase heater to be on when the system is off and the crankcase heater to be off when the system is on. You're also going to see some manufacturers will actually wire it to where the crankcase heater stays on all the time. I see a lot of three-phase systems, big compressors, they'll leave it where the crankcase is always on. Every manufacturer is a little different how they do that, but typically it's what you want to see. Crankcase heater is off when the compressor is on. When the compressor is on, the crankcase heater is off. Prevents refrigerant migration to the compressor during the off cycle.